Hi, class. This will be a walkthrough video for running IRT analyses for dichotomous data. In the video, I'm not going to go through very much theory behind IRT. We can talk about that more in class. This video is mainly just how do you run these analyses using the MERT package, and sort of how to interpret the output. So I would highly encourage you before you watch the video to read through the readings. But please watch the video and also try to run some of these analyses yourself before class. And we can talk about this more when we get into class. My camera isn't working, so you don't get my pretty little floating head here on the side. I think it'll be okay. So the first thing we're going to do is we're going to load our data set into R. So there's a data set on Canvas just called binary. It's saved as a SCADA file. It's basically, it has a data set. There's 750 observations. It has 6 variables, and the variables are just coded. So say this was a test with 6 items, and then the data set's coded 0 if they got the respondent got the question correct. I mean 0 if the question was incorrect, and 1 if it was correct. We're going to load the we're going to use the MERT package, the multi-dimensional item response theory package, and we'll use the psych package too, just to calculate some different classical test theory statistics, just to give us an idea of kind of what these data look like. We can use the describe function from psych, kind of give us an idea of what these data look like. So we see there are 6 variables. We can see the variable names here on the left side. And there's no missing data in this data set. We can see the mean here for question 1 is 0.78. So 78% of individuals got question 1 correct. And we can see question 5 would be the most difficult item. Only 65% of people got question 5 correct. And question 3 would be the easiest. 89% of people got it correct. We could also look at these as just response frequency, so you can see the data. You can kind of see how the data are coded 0, 1, and there's no missing data. We can also run the alpha command in the psych package, and it'll give us the overall alpha for the test, which is it's not great, but it's not terrible either at 0.69. But we can also get the classical test theory discrimination statistics from here. We could look at the R drop column here. And remember, this is the point biserial correlation between the item and the total score, with that item removed from the total score. So it's the corrected point biserial correlation. The R core here would be where that item is included in the total score. But this also gives us an idea of the item discrimination. We can see question 3 has the lowest discrimination, and question 4 here, it has the highest discrimination. There was also this item analysis function from the sjplot command that plotted out a nice little summary table of these statistics for us. And you can see there's all the same information in here as well too. So this should be good to keep up as we run through the same analyses or similar analyses in R. So the first thing we're going to do is we're going to run the rash model. So the rash model is probably the simplest IRT model. In the rash model, the probability of a correct response is a function of someone's latent ability. So they're the function of the latent trait and the item difficulty. The rash model assumes all the items are equally discriminating. So the rash model actually sets the discrimination for all items equal to 1. So we're saying the items don't, that they all are equally as discriminating between each other. Now, we're going to interpret both the item discrimination and the item difficulty a little bit differently in the IRT framework. The difficulty parameter is going to give us then where on the latent trait you would need to be in order to have a 50% chance of answering the item correctly. And so I think that'll make more sense as we run through this. And you probably already kind of understand if you read through the materials too. So the first thing we do is define our model. Sorry. Basically here we're saying, I'm gonna call this our rash model. We're basically saying here that our latent factor F is defined by variables 1 through variable 6. If we're going to use all of them, we can use a little dash. If you're going to use specific items, you can put commas between them here. So, latent factor F. And we could name this anything we want. And this is similar to how we declared our model in the CFA. The same things going on here. Then the next thing we do is we fit our model using the MERT function. Basically, we tell it our data set, our model, where we're using this rash model, the item type, and this time we're running a rash model, so we tell it rash type. It defaults to a 2-parameter logistic structure. So we want to use a rash model. I don't think I ever ran this. There's our model. We can fit our data. Here we go. It's converged. If we just call the function, it basically just gives us a lot of different fit information. Like here, we have the AIC and the BIC, which is good for comparing this model, the rash model to another, I guess, IRT model. We get the root mean square error approximation again, which we could also, we interpret it similar to other root mean square error approximation. So, less than 0.05 is pretty good. This G2 is it's kind of like a chi-square test of model fit, where, the null hypothesis here would be that the IRT model fits the data. So this would be one of those tests where we'd want to fail to reject the null hypothesis. And so since we reject it, it's probably saying that, maybe these data aren't a great fit to the rash model. If we want to get the coefficients, our difficulty parameters, and that's how you get your discrimination as well. We use the coefficient function, tell it the model you fit. We want you to report it in IRT parameters. And the simplify equals true just kind of puts it in a nice little table for us. You'll notice we can run it here, and you see it puts it in a table instead of, I think before, it like stats them. You can try it with false on here and see if you like that, how it views them. If we just wanted to get just the item estimates, we can get them. Here, notice the column A is the item discrimination. B are the difficulty estimates. G would be the lower asymptote for the guessing parameter, and U would be the upper asymptote for it. You know, the rash model, we assume that guessing doesn't have a big impact on whether someone would answer the item correctly. So, you know, the lower and upper asymptotes are at 0 and 1 here. So we can ignore those columns for the rash model. Notice the discriminations are all set to 1 in the rash model. The difficulty parameter here is negative 1.8. So what this is saying is that you would need a latent ability or latent trait level of around negative 1.8 or higher to have a 50% chance of getting that item correctly. That's how you would interpret it. And we can also see here, you know, the easiest item would be question 3. You would need a latent ability of around negative 3 in order to have a 50% chance of getting question 3 correctly. And question 5 would be the most difficult. Right, so you would need a latent ability of around negative 0.9 in order to have a 50% chance of getting question 5, of answering question 5 correctly. And that's similar, you know, it was the same thing we found here. Question 3 was the easy, in our classical test theory, question 3 was the easiest and 5 was the most difficult. But you see how we're just sort of interpreting them just a little bit differently. You know, the difficulties of all these are negative, so it's saying this test wasn't too difficult. You know, you would need below average ability levels in order to get them correct, which isn't surprising because more than half people got all of the items correct, right? You know, 78% got number 1 correct, 65% got question 2 correct. You know, sometimes it's easier to view these as a plot. You know, view a plot of what's going on. So we can get the item characteristic curves in here. We can use the plot function. You put the model you fit, type equals trace, gives the item characteristic curves. And then you can tell it which items you want to plot. So here we plotted all of the items. Notice the slope of all of the lines are all of the same. The only thing that's different is that they're shifted either to the right or to the left, depending on how difficult they are. So we can see here's just, what was this? Questions 3 and 5. And you can see how they're just shifted along the x-axis, depending on how difficult they are. It might be easier to actually view that. We can plot them on top of each other. If you add this facet items equals false here, it's a little bit easier. Then now you can really see how they're just the slopes of the lines are the same. But how they're just shifted. Question 3 is, you can tell, is an easier item. Notice when you're at an ability level of about average here, you have, what would that be? You know, about a 70% chance of getting question 5 correctly, and about 95% chance or something of getting question 3 correctly. Sometimes it's hard to tell, you know, from this graph exactly where you are. So I wrote a little function here. You can type where you can give it different values of the latent trait theta, and it will, and the function will tell you what ability level you'd have to be to get that. So let's see here. Let's run the function. So now the function's saved. And then we can call the function. So if we were at a theta of 0, So here for question 1, if you're at an ability level of 0, you have about a 96% probability of getting question 1 right. What was question 5? We were showing earlier you have about an 82% probability of getting question 2 correctly. So maybe, that's what we would try to, it's hard to tell on a graph, especially on a computer, moving your mouse with your hand. So I thought we could look if we were at an ability level of -1, we would have a little less than a 50% chance of getting question 2 correct, and a little less than 50% chance of getting question 5 correct, but we would have a 97% chance of getting question 3 correct. So that's how you interpret these difficulty parameters. And remember, question 1, the difficulty level was 1.803. Here, I ran it here just so you can see that if you're at that ability level, look, you have a 50% chance of getting that item correct. That's how you interpret these difficulty parameters. Sometimes I think it's easier if we can just play along and plug in different values of theta. And you can play around with this too. Theta of 0.5 rash parameters items, and we can get in what the probability of getting each item correctly would be. Notice it doesn't matter how large theta is, you're never quite right at, you're really close to 1, but that it asymptotes out at 1 and 0, so you never quite get to 1 and 0 there. Let's see. We can get the item information function. There's applied here. So it tells us, most of the, that the majority of information, say, for question 3 is really for ability levels, I would say, like, 0 to, -4 or something. Or, really any individual with latent trait less than 0 has most of the information for variable 3. Variable 5 here, most of the information is probably between a theta of 2 and -4, somewhere around there. Here's the information codes for all the items. Here's the test information function. So there's a graph with the standard error. So you can see the standard error of measurement is lowest for people that the purple line here is the standard error of measurement. Is the lowest really for people between, I don't know, around what, -0.3 and, maybe 0 ability levels on this test, which makes sense because this test, the items on the test were relatively pretty easy for all of these 750 individuals. So you can see the test as a whole has most of its information is found between ability levels, -4 and 2. And then if you just want to plot just the test information and not the standard error. So you can also get a 1-parameter logistic IRT model, which is mathematically equivalent to the rash model. The main difference is in the rash model, remember the item discriminations were all constrained to be 1. In the one parameter logistic IRT model, the 1PL IRT, we estimate the discrimination parameter, but we set them all to be equal across all of the items. And so that's what we're telling it here when we're defining a 1PL model, is that, you know, our factor is measured by variable 1 through variable 6. And we want to constrain the Merck calls the discrimination parameter A1. We're going to constrain A1 to be equal for variables 1 through 6 to all be equal, is what we're saying here. We basically estimate the model again. You know, here are fit statistics. If you notice, if you look at these from what they were before, you know, our G2 fit is the same. Our root mean square of approximation is the same. The AIC and BIC are going to be very similar because they're mathematically equivalent models. You know, we basically go through the same steps. We have to use the coefficients function to get our parameter estimates. And so you see here, you know, the discrimination parameter for the 1PL model, discrimination is estimated to be 1.65. So we estimate in the 1PL model. In the RASH model, it's just set to 1. So we can see, and then you can see, then here's the difference between the two. Notice the difficulty parameters are slightly different in here too. We still come to the same conclusions. So if we look here, question 5 is the most difficult. Question 3 is the easiest. That's the same thing we found in the RASH model. It's different because notice when we plot these functions that the slopes of the lines differ. So here is the 1PL model. The slopes are a little bit steeper because item discrimination is larger than in the RASH model. They're not as steep. So here I'm just flipping through. There's the RASH. That's the 1PL. And that's the RASH. So you notice that the ICCs are steeper in the 1PL model. You know, we can get our different data estimates again. You know, if we had an ability level of 0, we would have a 95% chance of answering the first item correctly and an 82% chance of answering the 5th item correctly. And if you wanted to notice the fit between the two models, you can see the fit is the exact same, you know, within rounding. The fit of both these are the same because they're mathematically equivalent models. It's just a reparameterization from one to the other. So we can kind of relax the assumption that all items are equally discriminating and actually estimate a discrimination for each item. That's what the 2-parameter logistic IRT model is. So it's a more flexible form of the 1PL or RASH model where each item has its own discrimination parameter. So for this model, you know, we follow the same steps we did as in the RASH and in the 1PL model. We define our model, and then we fit it using the Merck function. We give it our data set, our model, item type is 2PL. We can extract our parameter estimates and view them. So let's look at what's going on here. For the 2PL, notice that we have a different discrimination parameter for each one of our items, and not all of them are the same. Discrimination for number 1 and number 5 are pretty similar. Looks like 3 is the least discriminating, and 5 is the most discriminating. Is that what we found? Let's see, 4 was the most discriminating, 3 was the least. Oh yeah, 4 here's the most discriminating. Yep, and 3 is the least. So we still find, the same information. It's just, remember, they're just interpreted slightly differently. So what discrimination is going to do is going to look a little bit different when we plot them, is because the slope of the lines are different. So here now I've plotted in this our 2-parameter logistic fit. So these are the ICCs for our item characteristic curves for items 3 and 4. So 3 was the least discriminating, 4 was the most most discriminating. Notice that the slope for item 4 is a lot steeper than the slope for item 3. And also notice that they're shifted a little bit differently along the x-axis because their difficulty levels are slightly different. So now with items with similar difficulties are going to be, the difficulty is going to shift the item across the x-axis. The discrimination is going to change the slope of the line here. So here's one. So this is items 1 and 5 have very similar discrimination. So you can see that the slopes of the lines are pretty much the same, right? And if we look at 1 and 5 have pretty different difficulty levels, so they're shifted along the x-axis. Question 5 is more difficult than question 1, but they're equally discriminating if you see their slopes are the same. So, the discrimination suggests that, item 4 can distinguish between low and high examinees better than, say, question 3. See how question 4, we do a better job. It has a steeper slope, so it does a better job of discriminating between those with a high ability level and those with a lower ability level than, say, item 3, whose slope isn't quite as steep. Notice that it's running up to closer to the asymptote quicker than item 4 is. That's kind of what that's telling you. Remember we looked at kind of the item descriptives from, the 1PL and then the RASH model. We can think of the 1PL as being nested within the 2PL model that we could use in a likelihood ratio test to see, which model overall fits the data better. So we could use just the ANOVA function, and then we would get a likelihood ratio test here. So, it's just a chi-square test of the difference between the two likelihood ratios right here, this column. And we can see the likelihood ratio test is saying that the 2-parameter logistic model fits the data better. If we look at the AIC for the 2-parameter model, is smaller than the AIC for the one parameter model. Same for these other statistics. Notice what's going on here. Actually, the BIC for the one parameter model is a little bit smaller than for the two parameter model. So maybe there's a little bit of evidence there that the one parameter is better fit. A lot of times we kind of let the kind of the purpose of the assessment and whether we believe that each of the items should be just should the items discriminate differently among people or not, as here I consider it's like the theoretical assumptions or expectations of the assessment. Typically, the model with more parameters is going to tend to fit the data better. So a lot of times the likelihood ratio test will be significant. That's why a lot of times we also look at some of the other fit indices to kind of judge how much better. And it's really not that much better. In here also go through some different diagnostic assumptions checking. The two main IRT assumptions are unidimensionality and local independence. We could also say the RASH model and the 1PL model make it an additional something that the items are equally discriminating. But all the IRT models make an assumption that of unidimensionality, which basically requires that there's a single latent construct that underlies a set of items. Notice that. So we basically need to assume that there's a single latent construct. So this would be if we ran a factor analysis. A one-factor solution should adequately describe the relationship among these variables. And the local independence assumption, it basically says that once we've taken into account that latent trait, that there's no other relationship that exists among the variables. Like the only reason that the variables are related, these six items are related to each other, is because of that latent construct. That if there's any remaining relationship between the variables, that's a violation of the local independence assumption. The most common ways we typically test for unidimensionality would include doing like a PCA or EFA analysis, checking for differences between a one-factor or a two-factor solution or a multi-factor solution. You could also check this in a CFA. For both the EFA and CFA, we could check the local independence assumption from like the residuals of those analyses. Basically, we would want then that that factor then explains, if it explains the relationship among the variables, all the residuals should be pretty low. So as we want residual correlations less than 0.1. The MERT package has they call it, a Yin's Q3 statistic that's used to check for local independence. And so basically here it's giving you a correlation matrix. And so this is like our residual matrix here. The general rule of thumb I've seen is we want these residual correlations to be less than 0.2. So we would look in here. Here's a residual correlation greater than 0.2. You could also get raw and standardized residuals from your analysis here. I think these are the raw residual values. Here's a raw residual greater than 0.1. And these are then standardized residuals. So those are just different ways we could check the local independence assumption. A lot of times I see people check this from the unidimensionality test. You know, we fit a 1-factor. EFA, we tested against a 2 or 3-factor. EFA, the 1-factor fit the data the best, and that all has a bunch of small residual correlations. We can also look at how well the, you know, we can diagnose the IRT model at both the item and person level. You know, at the item level, the package has a bunch of item fit statistics. We can get, so let's say for our rash model, we can get some different fit statistics to describe how well each item then fits the IRT model. If we call it, we get a list, you know, for each one of our items. It gives us outfit statistics, standardized outfit, in-fit statistics, standardized in-fits, this G2 statistic, the p-value for it, a root mean square of approximation for it, and then a chi-square difference test as well. In-fit and outfit are only available. Those are rash specific fit indices. I believe there's a handout in the optional folder on interpreting these different in-fit and outfit statistics. You know, I've seen recommendations you want in between, like, you know, ideally, if they fit the model perfectly, the in-fit and outfit statistics will be 1 for each item. And I've seen, you know, suggestions you want them between 0.8 and 0.12 for a high stakes test, while others will say as long as they're between 0.5 to 1.5, then the items are pretty useful. You know, you get the standardized values here too. Although in our case, I'd probably just ignore the standardized values because they're pretty sensitive to sample size and generally not recommended when you have large sample sizes. I think the site I saw was greater than 300. We have 750. So these are all pretty large. But you would compare that to like a normal distribution. So, you know, anything greater than like 3 would flag as misfit. For, you know, the G2 and the chi-square p-values, these are again situations where the null hypothesis is that the item fits the model, so we want to fail to reject these items. You know, the G2, we rejected it for all items. For the chi-square here, you know, item 2, item 5 fit the data pretty well. You'd interpret these root mean square errors approximation, you know, similar. You know, less than 0.08 is good. Less than 0.05 is even better. You can read up a little bit more about these different fit statistics. A lot of times, you also see people looking at really empirical plots of the items. Gives you an idea then that if the data fit the model, then the, you know, empirical data points would fall along that item characteristic curve here. And we can see, you know, for item 1, I mean, even with these confidence intervals, most of them aren't hitting the line. You can see there it is for 2. Item 2 is not fitting well. Item 3, maybe. Item 4, you know. Item 5, it's not really following along there. Item 6 is doing a little bit better. So that's just a way we can visually diagnose misfit. So we can do it for each of the items. We can also do it for person. So there's a person fit command in the MERT package, which will give us how well each individual fits the rash model. And you can see here, so it's going to print out there's 750 people in the data set. It's going to print off a data set with 750 rows, which will give us our in-fit, outfit information, and then this ZH statistic for each individual. We can interpret our in-fit and outfit similar to how we interpret them in the item. You know, we want these around 1. Shows that the person fits the rash model. The ZH is a standardized index, and you know, when ZH equals 0, the individual's response pattern is perfectly aligned with the IRT model. And some general rules of thumb I've seen is that if it's less than -2, indicates that there's a large misfit between that person and the item. So we want to check out those individuals. For the person fit command, we were able to run it so we didn't have any missing data. If you did have missing data, you'd have to remove those items, refit your model, and then run person fit again before it would let you use it. We could get a histogram of the fit, so we can kind of see how the person fit kind of looks visually. We could add a line here at -2. So, you know, most of our people fit the model pretty well. We also don't have any extremely large values either, which is good. And very few people who aren't fitting the rash model. We could also, you know, get a, we're just looking for whether they're less than -2. I'm going to get a sum of those that are less than -2, and then get a proportion. So it was 5 individuals who don't fit the rash model. You know, in rash modeling, the kind of approach we take is that that if our data don't fit our model, we want to know, well, what went wrong in our measurement? You know, is there something wrong with an item that maybe we should remove that item from the model and re-estimate it, that we might get better fit. You know, but if you were doing it in an IRT framework, you would say, well, you know, the 1PL model doesn't fit the data very well. Does then allowing items to have different discrimination fit the data better? Where, you know, if you know, does adding a guessing parameter, that would be a 3PL model, fit the data better? Whereas in rash modeling, we want to then say, well, if our data doesn't fit the rash model, what went wrong in our assessment that it doesn't fit the model? So we want to diagnose it both at the item and person level, and we would probably remove those people and remove items that don't fit, so that our data then fit actually the rash model. We'll talk about that a little bit more in class as well. You can also estimate individuals' latent traits for each of the individuals. The MERT function has basically three ways of doing this. You can get a maximum likelihood estimation. You can get an empirical Bayes estimation that uses the mode of the posterior distribution. You can get an empirical Bayes estimation that uses the mean of the posterior distribution. It calls it, you know, expected a priori. EAP is how they do it. That's the default in in the MERT package. It's also the default, I think, stated defaults to this too. So, you know, the first one is basically we're going to use like a maximum likelihood estimation to calculate the factor scores. The downside to using this is any individual who got all the items correct or all of the items incorrect, we can't estimate an ability score for them. With using an empirical Bayes estimate, we can get we can get an ability estimate for all response types. So I think that's why a lot of them default to using the empirical Bayes estimation. It's an empirical Bayes estimate because we don't set our prior distribution. The prior distribution is being estimated from the data. That's why it's called empirical Bayes. In here, I'll also show you how the RASH model is really just a special case of a generalized linear model. And I also show you how you can estimate it if you just used a multi-level modeling package. I believe there's a there's a reading on one of the readings that also walks through how you can estimate it in, like, I think it uses the HLM package, how a multi-level model or a generalized linear mixed model, you can think of the RASH model as a special case of that. And so that's what I do here. We have to change our data from it's what they call wide format to long format. Well, you know, wide format, each row in the data set represents an individual, so we'd have 750 rows. In long format, we would have a row for each individual and each item. So we would have, there's 750 individuals, 6 items, so there'd be 4,500 rows in the long data set. You can play around with this and see for yourself how you get the same, actually we get the same, takes a little while to actually estimate it in LEM. There we go. And see, here are our RASH estimates, our difficulty parameters. Again, it's just the signs reversed from what we found in the MERT package. Here's how you can get the 2-parameter logistic model as a CFA. So, we can use the Laban package. We define our model again, same thing we kind of did in the MERT package. We would fit it. We can run our estimation here. So we basically do the same thing. We have to tell it that it's ordered data. And then here are conversion estimates to convert the CFA factor loadings and threshold parameters into item discrimination and item difficulty parameters. The one thing is the IRT discrimination parameters in Logits, we can convert it to a probit, which is what the or a normal octave is what the CFA is reporting. So you can see within rounding, we can see the difficulty is similar. And then, whoops, where was the, and we can get the difficulty items. We can see for number 1 is -0.98, there's -0.98 again. So within round, they're not going to be the exact same because the CFA is using a weighted least squares and this is using a marginal maximum likelihood approach. So, within rounding, they're going to be similar. Here's how we would get, the 1 PL model. As a CFA, we constrain all the factor loadings to be equal. And then, we could re-estimate the model, and there's your model parameters again. So that was just a quick run through of how you can actually run these analyses in R. We'll talk about this a little more when we get into class, but I wanted to give you something that you can practice with in the interim. Now, if you have any questions, shoot me an email, post to the message board. I'm here to help. Thank you.